we have information about this Nichols algebra, and we try to apply them in other areas and have certain, and for instance, there is some paper, new result about how, for instance, Bonnefer, Rouquier used this for construct certain categorification. And also they have important properties, the representation of this algebra. For instance, they are highest weight categories in some, with infinitely many objects. And another thing, they look very similar to the small quantum groups. And so we can repeat some of the ideas present in the study of representation theory of this algebra in our context. And also, we hope also to obtain certain information about of the Nichols algebra by studying the representation theory. Well, the aim of this talk is give you some tour around certain beautiful symmetry present in the representation theory of this algebra. This is a list, a short list of what I want to mention. Mostly they are not the results are not mine. It's more the other people, and just that to mention. So I will start by to define a little bit about the Drinfeld double. I will consider mostly finite dimensional algebras, and in this case, the Drinfeld double is a kind of double cross product between the dual and the original algebra. This means that the H dual acts in H and H acts in the dual with certain relation that allows us to define a new Hopf algebra over the tensor product of these two. For instance, in the case of the group algebra, the dual of the group algebra is the algebra function over the group, and the multiplication is given by this rule. The group-like elements commute with the canonical basis of the dual in this way by conjugating the elements. This is the first example. And the other ingredient of these Drinfeld doubles are the Nichols algebra that was already defined by Nichols in his talk, and also Dirceu talked about this, and he also defined the Jeter-Drinfeld models. I only will say that we can, it's equivalent to see a Jeter-Drinfeld model. It's equivalent to have a model over the Drinfeld double. And the Nichols algebra is, in particular, is a quotient of the tensor algebra. And they talk about example over abelian groups. I give you an example, the first example over a non-abelian group. What is the Fomin-Kirillov algebra? This is a Nichols algebra constructed over the space of transposition in the symmetric group of 3 letters, where we have this the action of the Drinfeld double is given by commuting and acting by the sign, and these are character elements with character AG, with the character of the transposition. Then the Fomin-Kirillov algebra has this presentation by generated relation. With this relation, we define the Nichols algebra. This is called a Fomin-Kirillov algebra because this was first defined by Fomin and Kirillov in the context of Schubert varieties, and then Milinski and Snyder, they proved that it is really this Fomin-Kirillov algebra are Nichols algebras. And one can define these algebras for any symmetric group, but we only know that are finite dimensional for case N3 for the symmetric group and over 3, 4, or 5 letters, and for the symmetric group on 6 letters, we didn't know if it's finite dimensional or not, and we didn't know the presentation of the Nichols algebra. So, well, here I write some some property of the Nichols algebra that are interested. For instance, as I said before, we will consider finite dimensional algebras, and in this case, as it is finite dimensional, the Nichols algebra has a maximum degree, and this component is turned to be one-dimensional because every Hopf algebra is a Frobenius algebra, and a Frobenius algebra is an algebra with some not degenerated bilinear form, and this allows us to, or one can show using that the maximal degree will be one-dimensional. For instance, I fix one element in the top degree. And if one considers the dual of this element, one can define a non-degenerated bilinear form of the Nichols algebra, and then one can show that the Nichols algebra is symmetric, or the Hilbert series is symmetric. Here I remember what is the Hilbert series, what counts the dimension of the homogeneous component. And now here we can draw in this way a Nichols algebra because the symmetry of the Hilbert series. Okay. In the case of the symmetric and the Fomin-Kirillov algebra, the Hilbert series is that, and here we know very explicitly the basis, and it is a small case, not it's a 12-dimensional for the Fomin-Kirillov algebra over S4 and S5. We have in the S5 we have it has dimension more than 1 million. I think I don't remember exactly. 8 million. Okay. So yeah, it's too difficult to write down here, and I introduced this new object associated to the B, which are considered as the Nichols algebra for the Nichols algebra, because it will appear in the next slides in the definition of the Drinfeld doublet that we are interested on. So I recall that we are interested in this Drinfeld doublet, which is the Drinfeld doublet of a Bostonization. A Bostonization is just a crossed product between H and the Nichols algebra induced by the action of H of the Nichols algebra. So we have it's a twisted tensor product, for say quickly. So from now on, I will denote by D this Drinfeld doublet. And here is the main properties that allow us to prove the main properties over this Nichols algebra to prove this symmetry that I will mention later. And the first thing is that a Drinfeld doublet admits a triangular decomposition. That means that as a vector space, this is an isomorphism as a vector space. The Drinfeld doublet is the Nichols algebra, tensor the Drinfeld of H, and tensor the Nichols algebra of this element, this object that I introduced before. The thing is, it is another Nichols algebra. And also, it is graded, and the graded is induced by the Nichols algebra, because the Nichols algebra is a graded algebra. And the other thing, it is a symmetric algebra. That means it has a not degenerated bilinear form, symmetric, which is symmetric. And I will point out here that this triangular decomposition allows us to think on the representation, to study the representation of D by meeting the technique or ideas what are present in the study of the category BGG, the representation of a Lie algebra, the BGG category O, where in our case we will consider this Drinfeld doublet here in the middle like a Cartan subalgebra, and these two subalgebra, this as a Borel subalgebra. So I mean that we will consider this like a positive part. This and I will use this in the next field, in the next slide. So what this is a result that proved the Bellamy and Thiel for any algebra with a triangular decomposition. That means that it has this decomposition as vector space, and also it has is graded. So for any, but in the special case, in our case, it's this way. If H is semi-simple, and then the category of grade D module is the highest weight category whose set is this lambda. Lambda is the set of simple module over the Drinfeld double of H times C, and C what the play of C is degraded. I mean, if H is semi-simple, then the Drinfeld double also is semi-simple, and then every module over the Drinfeld double, it will be the direct sum of simples of elements in this set. And if we consider the graded category, we only have to move these simple modules in the shifting the degree. And for this reason, we have this set of weight a little bit more, several bigger than this other one. Yeah. No. H semi-simple characteristic is 0. Yeah. Yeah. You are right.
What's the order on the set of weights?
The order is induced by the order in C, on C. And it really is a highest weight category in the meaning of Rouquier, I think, but not in the meaning of Carl Partial Scott, porque Clem Partial Scott they define a highest weight category for finite sets of weights. But here we have infinitely many weights, and also the other property that is not good is that if you fix a weight, we have infinitely many weights lowers because of C, and this is not good property for cohomological aspect.
Well, it should have infinite global dimension, right?
Yeah, because it's symmetric. Yeah. And well, the ingredient of a highest weight category are the weights and the standard model. The standard model are just these induced modules. And once you have the standard model and you know it is a highest weight category, you have a classification of the simple modules. Here a picture of how the standard model looks like. And I point out that these standard modules are isomorphic as a vector space unless as the Nichols algebra time the weight lambda because we are tensoring over this positive part. And by the triangular decomposition, this killed all the positive part in the left of the tensor product. Okay, another thing is that to be more clear of what is this induced module, I would say that the positive part acts by 0 over lambda. So here the action of the positive part on lambda is 0. And I say before that with this idea we can try to imitate the idea of the representation theory of Lie algebra. We have another problem that it's more difficult to make computation in the example is that these weights, the simple modules, can be of dimension bigger than 1. And what happened in Lie theory is that all the weight has dimension 1, but here it could be more bigger. But here another example of a symmetry that we have a Hopf algebra. We have that the dual of we can define duals. The duals are also modules over the Drinfeld double. And what happens is that the dual of a standard module is again a standard module over the weight in the bottom of the Vermeer modules of the standard module. And the simple module are also, if you consider the dual of a simple is again a simple, and the simple is the simple attached to the weight in the bottom of the simple module. Well, once we have a classification of the simple model, a natural question what would arise is to try to describe the character of the simple models. The character in this case is a graded character. As is semi-simple, the Drinfeld double of H is semi-simple. We can consider any object or any module as a direct sum of modules, where here A means the degree, and then the character is the sum, is the polynomial over in this over lambda, this Laurent polynomial. This t to the e, say which is the homogeneous component, and character of this means the class of this DH module in the categories. As we have finitely many simple module over the Drinfeld double, we can associate it to any object here, an element in the character. Yeah, this is the element in the Grothendieck ring of the Drinfeld double of H. So that is a difficult question, we know, of course, and I don't hope to answer this in general case, but there is some recent result of Yamane. He proved he gives some formula for the graded character for some weights that he called typical, and this is called for Nichols algebra of diagonal type. I will point out here another element of symmetry in this case that was already mentioned by Nicolas, what is the Weyl groupoid. The Weyl groupoid in the Nichols algebra diagonal type is induced by some isomorphism, Lustig isomorphism. There is in the diagonal type, there is some Lustig isomorphism. These are algebra isomorphisms between these Drinfeld doubles. Between another Drinfeld double. There is some bijection. One can define a bijection here in the over V in such a way that these are Lustig isomorphisms. These are Lustig isomorphisms of algebra, and this isomorphism what induce isomorphism in the standard model and induce isomorphism in the simple models that allow to Yamane to put all this information, combinatorial information, in this formula, like in lead theory. Okay. What follow? Okay. I will talk about a little bit about BGE reciprocity. There is this is all the result on Holmes and Nakano, and also was proved by Bellamy and Thiel again, that if you have an algebra with a triangular decomposition, you can, for any projective module, find and a standard filtration. That means a filtration of modules such that every subquotient is a standard module. I proved this using for the case of Hopf algebra, using strongly the property of the Hopf algebra, but later Bellamy and Thiel, they proved this in general, and it is not needed the property of the Hopf algebra, and also they cite a result of Homer and Nakano that older that is the same. And what's the VGG category? The VGG reciprocity say that the number of subquotients in a standard filtration, which is isomorphic to a fixed standard module, is equal to the composition factor of this standard module of type L lambda L lambda. So this is the relation between the projective and the simple of the. This is the VGG reciprocity. But as we have a graded category, we can also think on this reciprocity in terms of the graded category. And also we have a graded standard filtration. That means that the filtration here, we can consider graded submodules. And in this case, the VGG reciprocity is like an equality between Laurent polynomials. Yeah, and this Laurent polynomial exists because the standard modules is the basis, or the graded character of the standard module form a basis of the graded character of projective modules, and also the graded character of simple module form a basis of the character of any module in the category. So you can find these polynomials, and then you can prove that this, it's not necessary to find it, but you can prove it that it's called. This is one of the symmetry that I want to tell. And another is this about the symmetric Hilbert series on the simple models. Let me start by some examples. If you consider the Drinfeld double of the Taft algebra, where the Taft algebra is the smash product between the truncated polynomial and the cyclic group, all the simple models are the Hilbert series of the simple model are in this way, and easily observe that they are symmetric. In the case of the Fomin-Kirillov algebra, we have 8 weights that are the simple module over the Drinfeld double of S3. And the Hilbert series is that we explicitly compute the simple modules over this Drinfeld double in a paper with Barbara and myself, and from there we can read easily that. Here, this one is the dimension of the trivial representation, and the term in degree 0 correspond to the dimension of these simple modules. And this is the name that we put to the simple module or the weights. And here appear the Hilbert series of the Fomin-Kirillov algebra, because for the other weights, here is lambda different to these 4. In the other way, the simple module coincide with the standard models. The standard model are simple, and for this reason appear here the Hilbert series of the symmetry group of the Nichols algebra. Here there is another example, was computed under Skevich and Mejia-Ranz. They computed the simple model explicitly in this case, in the Drinfeld double of this Nichols algebra times an abelian group. And I take this image from the PhD thesis of Carolina, and she draw the simple model in this way, and we also see in this picture that the Hilbert series are symmetric. Gamma is here in this case. Gamma is a preceded abelian group, but they proved they give an explicit. They compute explicitly the simple modules for any gamma. Is the structure, the dimension and the radio dimension is not depend of the group. It's basically all the same.
Wait, so how do you see this? It doesn't look symmetric.
Sorry? Yeah, this dot means the number of elements in the basis of the homogeneous component.
But you said it's symmetric.
Yeah, because you have to see the symmetry in this way.
Yeah, one,
right?
two.
Here you don't see, but it's 3, and you have here 5, and here other 5.
Oh, I see. I see. So on the bottom there's 3.
Yeah.
Oh, okay.
And in this case, there are 48 different simple models, I think, or more or less. And here is the picture only of 3. So one can ask it is a general phenomenon if every simple model has symmetric Hilbert series. So I didn't know that this phenomenon also.
Are they unimodal also?
Sorry?
Are they unimodal? Unimodal.
No, I don't.
In other words, did they grow for a while and then shrank?
I don't know. Maybe yeah, but if I can prove that it's symmetric, I will be happy. And also, Uri Tial posed the same question, but the restricted rational Charinic algebra that there are certain algebra with triangular decomposition. Stefan, you will talk about Charinic algebra, I suppose. And he proved that for certain case, this symmetry hold, and there are counterexamples where it is not hold, but it seems to be that it's a general phenomenon, or could be a general phenomenon under the correct assumption. Also, it is in the case of Lie theory, I think it is the Poincaré duality that the Hilbert series of the simple model is symmetric. And I think it is a consequence of a cohomology fact. When you see the simple model, like using intersection cohomology or something like that. Okay. Well, the duality is when I try to, if I we are able to prove this symmetry that I couldn't, but I was reading so much, and I found this also. This another symmetry which hold for any symmetric algebra. This symmetry hold for the Tate duality, what was defined yesterday by Julia Petsova. And there is also this symmetric, and then this also hold for the Drinfeld doublet, because the Drinfeld doublet are symmetric algebras. And I put this because it's the reference that I found, but maybe it is proved by other people, I don't know. Well, and I am looking about this because as in the Lie theory, you prove the proof of this symmetry is using cohomology. Well, I will looking for symmetries in the cohomology of these algebras. Okay, for that, I think I have so much time. Yeah, I have a lot of time, and almost finished. Braided autoequivalence. Braided autoequivalence is it's an autoequivalence of braided categories. And the difficult problem is to compute the group of braided autoequivalence of the center of the fusion category, what is the same that compute the semi-simple invertible AB module categories. And that is the Brouwer-Picard group of a fusion category. In the case of, if you consider the module over a semi-simple algebra, or semi-simple Hopf algebra, then the center is the Drinfeld double. And it seems to be that it is difficult to compute and also to find example of this braided autoequivalence. And in our example, it appear naturally one, unless in this example of the Fomin-Kirillov algebra, we noted that there is this natural bijection induce a braided autoequivalence in the category of DS3 models. The natural bijection is if you consider a simple model whose highest weight is lambda, you can send the highest weight to the lowest weight, which also is simple. So this induces a natural bijection in the set of weight. And in the paper with Barbara, we computed that explicitly because we computed explicitly these simple models. And we never know what is the meaning of this bijection. But in another paper, a referee, he or she told us that this corresponded to the unique non-trivial braided autoequivalence in the category of the DS3 model, the model over the Drinfeld double. And this was proved by Lettner and Priel and Nichols and Riepel. And in different papers, they proved they compute explicitly the group of autoequivalence, braided autoequivalence. So another interesting question is also this: if this bijection if this is a general phenomenon.
Yeah,
If,
do you have another example?
no, I have to do the computation in the case of the UFO algebra. The other to see if it is also hold there. I suppose yes, but there are so many simples that I have to sit down and write and do the question, the computation. Well, I think that that is all. Thank you.
If you have a semi-simple Drinfeld model of a non-abelian group,
Mm-hmm.
with a finite dimension and Nichols algebra, then these are classified by
Yeah.
Heckenberger and Benjamin, and they do have such Lustric isomorphisms.
Yeah.
Do you know how these isomorphisms enter into the picture of the representation theory?
One can try to see if this the paper Heckenberger and Yamane, using this Lustric isomorphism, they induce an isomorphism between different standard models, and then one can think if this also holds for this other Lustric isomorphism, and it would be interesting to know because. Among other things, Yamane used this automorphism to prove these formulas that I posted before, and also are useful to prove this Shapovalov determinant in the case of in the Abelian case. But I suppose it's interesting to work on this.
So there's a Shapovalov determinant formula for
Yeah,
certain cases?
for the diagonal case.
And so you know in particular what are the you can use that to decide about,
When the standard model is simple. With
what about, you don't know, you don't get an algorithm for computing you don't get like a Janssen sum formula?
For the Shapovalov? No. They give a precise formula for the Shapovalov determinant. You can compute it, it's very precise.
Does it have a denominator or is it cancellation free?
Sorry?
That formula, does it have a denominator? Is it a product or is it a product with no denominator?
For the Shapovalov? Yeah. No, it's a product. there is no. There is some. Because the Nichols algebra diagonal type you can depends of some symmetric bilinear form. So there are the formula is put all like a product. There is an -1, but it is something precise. What is the inverse? There is no denominator.
I'm just wondering if you look at the simple modules with dimension 1,
Yeah.
can you put any correspondence to, for example, if it was a Hopf algebra?
Yeah.
generated?
Because in Hopf algebras, the one-dimensional modules correspond with the group-like element of the dual.
Okay.
And Radford, in the paper, in all paper, he classified which are the group element of the dual. You can compute explicitly which are the group like.
And what is the interpretation of the higher dimensional modules?
No, it's just a model, one-dimensional model. But I think it is no. And there is some in the paper of Velamentiel. It seems to be that the model which are important in the characteristic algebra, I don't know in this algebra are the simple model which coincide with the dimension. The simple model is exactly the simple model over the of the weight. In this case, they are interested in this simple model because they give me some information, but I don't know so much.
Okay. Thanks.
Okay.